Thanks everyone for coming. One of the final sessions of the day. My most favorite topic in this industry. That's why I'm here still in my, I think it's the 17th year now that I get to witness another year where we say, next year it's happening, next year it's gonna come, the big hockey stick. It's difficult times at the moment, very interesting times, but what keeps me going, what makes me extremely optimistic about this industry is the startup entrepreneurs that still have the passion and the big conviction to develop stunning applications for additive manufacturing and stunning tools. And 4 of our most favorite tools we have, or entrepreneurs who are developing tools, we have invited to present their business on stage. We have 4 pitches coming up, 5 minutes each, and an opportunity to ask questions afterwards. So make sure that you think of something and challenge the entrepreneurs to make sure that they show you how competent they are in the next half hour. The first candidate to pitch her business is CEO and co-founder of nebumind, Caroline Albert. Welcome to stage.
Hi everyone, my name is Caroline. I'm founder of nebumind, and it's a pleasure to be here today. I would like to present to you our data analytics software, which helps manufacturers build the factory of the future, fully automated and self-regulated. Here we go. First, a brief introduction to the company itself. We started nebumind end of 2019. That's my co-founder Franz and myself. We had been working at Airbus before together, and we built up a subsidiary for Airbus in the field of sensor technologies. And at that time already, we had the challenge, well, there was a lot of data, but we didn't use it. And that's exactly what we want to change with nebumind. Today we have 13 employees, and in the last 4 years we have conducted about 32 projects with customers from different industries, and we work with partners in various technology fields. Back to the factory of the future. Everybody is talking today about the smart factory, and first projects are already successfully implemented. The focus here lies primarily in the automation of specific processes. So data is collected, for example, to replace pen and paper or to make production planning more efficient. The real challenge, though, which makes a production not only automated but really smart, lies in the concept of self-regulation. To achieve self-regulation, a company or a production needs to have its eyes and ears in every manufacturing step. It needs to monitor the quality, it needs to understand influencing factors, and it needs to be able to counteract if necessary. Today, we still have a long way to get there. The central problem lies in the different data formats in which today machines and sensors generate data. Pictures, graphs, Excel files. Today there's no possibility to merge these different data formats in such a way that you can analyze them together. And this makes a truly smart factory where all production steps are connected and communicate with each other simply impossible. This is exactly where we come into play. The nebumind software gets the data directly from machines and sensors in their various formats and maps them on the manufacturer component, creating a digital component twin, and therefore creating one common format. So the software knows exactly for every position in the component, the software knows exactly what happened in the production. For example, if the milling machine was moving too fast in a very critical area of the component, which will later on lead to geometric deviations, and therefore we already know now it will be a scrap and therefore stop the process. So with the nebumind software, productions get an all-inclusive information source for every component at hand. And only with this data consolidation, we create the necessary transparency to start self-regulating processes. in the following video, you get a first impression of the software. In this case, data is collected from a 3D printer and merged in the nebumind software. So temperature values, images from a thermal imaging camera, or oxygen level in the chamber, all data is projected on the component as a digital twin. The software can then show anomalies and their root causes online and can counteract if necessary. So we detect defects early in the printing process, or in the best case, even prevent them. The software is already used in different pilot projects. One of them is ESA's Aerospace, a space manufacturer printing components over several days. At the moment, defects can only be detected after the printing process, and of course, if a defect happens already in the very first layers, this is a huge cost and time factor for them. So we help them to connect their printers and merge the data in our software. In a very first step then, we processed the powder bed images with an AI algorithm so that anomalies in the recoating images are automatically detected and shown to the user so he can stop the printing process in time and therefore find the defects or the scrap early. Sorry, this was too fast. So this was a quick win for ESA Aerospace. What we focus now on is we fuse all kind of data sources in our software and in a multi-variable machine learning model, so to also identify correlations between different sensors. The ultimate goal, of course, is to monitor critical parameters simultaneously online and in specific cases to let the printer self-regulate. To summarize, well, as you have seen, we create a foundation for a highly or a fully transparent factory, and we help you to work towards a fully connected production. In particular, we help you to analyze process parameters in order to get a higher process understanding faster. We help you to monitor process parameters online to detect defects early. We help you to optimize your processes, which is especially important when you talk about industrialization and about ramp up. And eventually, we try to predict anomalies and therefore prevent them in the first place. Thank you very much for your attention. I'm looking forward to your questions and any discussions on Smart Factory later on and at a glass of wine. Thank you.
Thank you, Caro. Pretty cool story. I think that's absolutely required to finally produce highly critical, mission-critical end-use parts. We have to know if they have been manufactured right and how to optimize the outputs. The one question that I have is that image recognition in powder bed processes is not something new. I have seen a pitch or two in the past.
Yeah.
What do you do differently?
That's true. I mean, we have seen also, or there are several developments. We haven't really seen so many in action, to be honest. And I think it's because it's not very trivial. You can't take one AI algorithm and use it for every customer, for every use case. You need to do some adjustment. Mm-hmm. And this adjustment depends on what material is the customer using, what machine type does he have, what camera is integrated in the machine, or even also the quality requirements of the customers are different. And you need to do a lot of fine-tuning on the algorithm, which is mostly done manually then, so quite a time. We identified a way where you can very fast and very easy fine-tune the algorithm. So that's why we can access a broad range of customers and a broad range of use cases with different requirements, and therefore create a scalable product for that. Cool.
Exciting. Thank you very much. I'm sure there are tons of other questions, but let's save them for the drinks afterwards. Thank you very much.
Good. Thank you.
Next up on stage is a company that I really, really like. because they have answered my call for this industry doesn't need more different hardware technology. We have so much technology out there already. Let's make sure that we use that technology in the right way. Here's Christian Fischer from Headmade Materials. He's the co-founder, and he will tell us what Headmade Materials does. Thank you.
Thanks a lot, Arno. Yeah, the power of cold metal fusion. So the company is called Headmade Materials, and it's in there, materials, not processes, not machines, materials. And we called the so-called cold metal fusion technology. And with cold metal fusion technology, we wanted to create a technology not only for prototyping or 10 parts a year or something like that. No, we wanted to create a real production technology, and how we have done this, I will tell you. So first, a statement to the GAM industry at the moment. 3D printing is no rocket science for legacy manufacturing. Yes, it sounds that easy, doesn't it? But there is this rocket science in there. We heard a lot about rocket parts, so for space and for rockets, and the industry has done a lot, and there was a lot of money, and they developed the technology more and more. So this was a good thing, but in the end, it's not rocket science. It's not only space out there. There's a lot of industry out there with much higher amount of parts they need, and this is something we have to solve with our technologies. And to make legacy production, series production, this is no rocket science. If you think about production, and this is, I think, the most important thing, don't design parts for only the use afterwards. No, design it for the process. You have to design it for the process. And in our case, this isn't different. So, what are the things we can do with technology from us? So we can do impellers, for example. So the pump and valve industry is a very big industry. They are asking for big impellers. They want a uniform surface quality. They want high performance material like titanium, Inconel, and so on. This is something cold metal fusion can do very good. So we love this type of parts, and especially the type of materials, the not only stainless steel. There is another approach. So the tooling industry, or the tool and mold industry, you can do a lot by just thinking about your process. They have to be precise. Okay, now such a technology is not as precise as milling, for example, but if you combine it, you can do something. And this is a product we generated together with our partner Mim Plus out there. You can watch it there. These are very, very, very good opportunities you can do with cold metal fusion. Another one stands for itself, bikes. It's not the biggest thing, but it's the most sexiest thing. So I like this picture. Everybody likes bikes. So you can do very cool thing, very nice designs, and that's not only for bike, it's for fashion, it's for, you can use it for so much more industries, and because you get the prices down with the technology, you're able to generate customer products, not only defense and space or something like that. How we are doing this? So we are Headmade Materials. We just generated the material, and we combined two worlds. First world is the selective laser sintering machine world. So there are a lot of providers out there building laser sintering machines for plastic. That's important. The PA12 printers, if you want so. And we combined it with metal injection molding. Metal injection molding, solvent debinding, sintering. And that's it. And this makes us very fast and very strong in our development, because with this, we are only the material provider, and the whole technology is already out there. So we have these partnerships together with we called it Cold Metal Fusion Alliance. So with a lot of industry knowledge about, debinding and sintering, the big magic thing behind this binder-based technologies. This is quite easy to handle because we can use their existing technology. We don't have to adapt anything because our material is as close as possible to their specific already existing process for production. And this makes things easy. So to summarize this, why Headmade Materials? Why cold metal fusion? Why nothing else? And this is because of the repeatability. Repeatability is the key for every production. So you need a uniform shrinkage, you need a homogeneous shrinkage, and a repeatable shrinkage. So this is very important. You need to have a broad window, process window, the equipment can deal with. The next thing is scalability. There are different companies, you saw them, and there are many more. There are many more companies, and you can buy small machines, very fast machines, very flexible machines, big machines, and you can combine it. You can really combine it. The reliability is something else. So downtime in serious production is a much bigger problem than when you just do a few parts a year from, I don't know. This makes a big difference. The companies, they have to be able to deal with maintenance, with support, with all you need for these production cases. And all in all, this gives you the flexibility to not use an existing machinery and do something which doesn't fit that good on this machinery. No, this gives you the flexibility to really think about, or to really think in applications. To take your applications, design your applications, optimize your application, and afterwards you can streamline your process downside and be able to produce really economical parts. And this is what cold metal fusion is for, and this is what we would love to do with all you together. If there are any ideas, I think afterwards there's beer. Would be great. Hopefully we have some meetings, grab a beer and talk about this topic. Thank you.
Thank you. Thank you, Christian. Maybe one question from the audience. Is there a question? If not,
it's on you.
we have seen a couple of use cases. Is it complicated more complicated to design for this technology? What do you think is needed to really design parts for CMF?
I would say it is nearly as complicated than for any other technology. It depends on the application. With old technologies like injection molding, like milling, like casting, what's out there, they learn for decades, if not centuries now, how to deal with this technology and where are the borders, where are the advantages, the disadvantages of such a technology. And this is something. I think the last decades we played a lot. We made crazy parts. We thought we will be never able to deal with it, but now we have to come back to process design, and this is something I am missing at the moment. And when we have the ability to talk about this process design, not say, hey, this design is freezing, please print it. If we really have the ability to talk about the design, then there is a big chance, and in the end, we are no rocket scientists, so it's quite easy.
Mm-hmm. All right, cool. Thank you very much. There are 3 questions from the audience about why CMF, if there's binder jetting or MIM or versus LPBF. I think that's something that we will leave for the beer. You have a couple of really good answers for this, but feel free, reach out to Christian, have a beer with him, and he will tell you everything about it.
We have done a lot of things, all the others failed, so I will tell you by a beer.
Thank you.
Thanks.
So at AIM Ventures, we looked at almost 3,000 startups in the last 9 years. Every year, last year it was about 400 companies that applied for funding at AIM Ventures. And every now and then we get parts sent to the office. And it's really cool because you don't know what's inside. In most cases, I can immediately tell how it's made and how it was oriented. But a couple of years back, I had a little metal part on our coffee table in Starnberg, and I realized that it's spectacular aluminium. It looks like extremely quick build, a pretty fascinating technology, but I could not tell what it is. But now we have Jonas here, who is going to tell us. He's the co-founder of Valcun, and I'm really excited to hear his story. Welcome, Jonas.
Thanks for the introduction, Arno. So yes, the coming 5 minutes I will present you the solution for deployable metal additive manufacturing. Not because it's fun and a challenge, by the way it is, but also because there is a need from the manufacturing industry. And I think that was confirmed already from the talks this morning. So what's top of mind for general manufacturing is the supply chain resilience. And I wasn't aware of certain numbers, but maybe you remember like the blockage of the Suez Canal. It turns out that's like $9 billion each day that the economy loses. And that's just crazy. And also if you look, for example, downtown of manufacturing, just on average, each hour it's $260,000. That's just crazy. So that means that there is really an issue that needs to be solved. Also, if you look, for example, towards the metal workshops, they need huge amount of storage and inventory for having different materials and shapes to make parts efficiently. And efficiently, I'm saying even then 50 to 60% is being chipped away. So that are, I mean, I don't have to convince you reasons where additive manufacturing could benefit or provide value. But the main problem still is the deployability, to have it integrated in an efficient and economical way. And again, this was also tackled in this morning's sessions, because the technologies today, they still suffer from doing that by the use of chemicals, the use of feedstock handling, meaning that you need personal protection, so that increases the costs. So we are actually providing you this solution by a technology where we don't use powders, we don't use debinding, we don't use sintering, and we don't need a special environment that is ATEX certified. To give you an idea, the printer is just in a regular office at Valcun. And moreover, okay, we are focusing on aluminum at this moment, and we can actually tackle the highest strength aluminum alloys, the alloys that actually the industry wants. So I won't bother you too much about the technology because I will give a talk tomorrow as well, so we will go more in depth. But just to give you a brief idea, and that's actually explained to you, Arno, how it was made. So we start from a wire feedstock, and then we feed it to the print head, being fully molten, and we extrude it through a nozzle to build up the parts. And actually at the right-hand side, you see the real-life printing of it, to give you an idea. But let me demonstrate the economical deployability by a business case, because that's important, and it was a hot topic already today as well. So for this, we have a catalytic converter for air purification. So basically, you have a substrate, and then a certain catalytic material is put onto that. But that's a very expensive material. So actually optimize it for flow, and chemical reaction can actually significantly reduce the costs. And it seems like a very niche market, but it's actually a very big one. So you need several thousands of these parts in different sizes depending on the customer. So what we did, and this company is called AdCat, so they saw the value in this, in trying to do so, but they needed additive manufacturing for that, for the complex structures. So we were able to actually compare to the other metal additive manufacturings like binder jetting, powder bed fusion, to reduce the cost by a factor of 8 due to our process and the whole workflow. So that's interesting in terms of serial production, but even more interesting is that with our technology, we don't have the possibility, not only do we have the possibility for serial industrial production, but we can actually we have still several verticals to explore. For example, printing in space, okay, that can be just cool, which is it, by the way. But for example, by demonstrating the gravity independency of the process, so what we did here at the right, there we actually show that we can print upside down. So the first step towards gravity independent printing. So it was done together with ESA, but that also allows you on earth printing in all dimensions. Apart from that, so all the metal is molten in the print head, meaning how it's added doesn't really matter. So we can also work towards recycling, sustainability of materials. The fourth one is integration of robotic arm, and that's partially already demonstrated by the video at the right-hand side, meaning we can print very big structures or integrating in production lines like you do with welding robots. And the last thing is when we can implement it on a robotic arm, we can also implement it in a CNC machine. So working towards hybrid manufacturing. So there are many things we can still explore. So I'm doing like this not because I'm nervous, but because I'm so excited. There are so many other things to do. So some people say that the sky is the limit, but actually for us that's not true. Space is. So thank you very much.
Thank you very much, Jonas. We have 2 questions from the audience. Let's use one. Can I use the same slicing software as for my Prusa printer with Valcun technology?
We indeed start from such software, but like in polymer FDM, when you have certain features reaching a certain corner, you need to do something to make it work properly. And the properties of metals are different than for polymers. So we need to change the algorithms behind those features. So not directly, you can use it.
Excellent. Thank you very much. Thanks, Jonas. All right, last but not least, the most spectacular 3D printing technology right now out there, in my opinion, is a technology that is fairly new, transparent liquid, and like magic, something starts to exist in this bath. Luckily, Germany, or specifically Berlin, also has its own startup in this direction, doing fantastic research, building great machines, xolo, and it's being represented by Arpita Roychoudhury. Thank you very much.
Thank you so much, Arno, for the kind introduction, and I'm delighted to be here today representing xolo. So the company's name comes from the technology xolography that we are exploiting to do 3D volumetric printing, and today I would be talking with the focus on bioprinting. So far we have heard a lot about metals and everything, so moving on a little bit towards the medical and biomedical applications. This is where I come in xolo as the innovation manager focusing on the bio applications. So at the moment with the conventional 3D printing, we have 2 major pain points that I think where we can leverage and make life easier in medical technologies. Number 1 being cell viability. So due to when we do the regular bioprinting using jet spraying, so it has to pass through the nozzle, and that's where there is a lot of stress to the cell, and then also the number of time it needs to go through the printing cycles. So we lose a lot of cell due to this, and they die, denature, and cannot be used towards the end. Number 2 being the limitation in the design of freedom. So when we are doing layer by layer and gluing those layers on top of each other, what happens is that we are architecturally and geometrically limited in how we want to design those complex organic structures, which we will somehow try and see that how xolo tries to tackle those, and also the resolution of the printed objects, which goes multi-times higher with the xolography. So these are the pain points we are tackling at the moment. And as Arno mentioned about the magic, so this is what happens. So this is a cuvette. Sorry, I think I skipped a slide. Sorry. It doesn't go back? Yeah. So what happens with xolography basically is that we are printing inside a cuvette. So in the vat, so it's a sterile, non-contaminated environment throughout. It is not coming in contact with the atmospheric dust, dirt, any kind of contamination. There is no sedimentation. It's a homogeneous resin with the photoinitiators, dual color photoinitiator, which we synthesize in xolo as well, which are fairly less cytotoxic than the others available. So there is no support structure. We don't have layers in the printed objects. So wide range of material properties in terms of hard to viscoelastic, mid-range, until very soft materials for bio cell culture, etc. we have been using, and more importantly, that the biocompatible materials, and in our next generation of the Zube, the product is called Zube because of xolography, and we have the temperature control chamber inside the printer, so where we can ramp up the heat and cooling cycle depending on the physiological condition of the cells or any other biological sample that we are using. And that's the video I wanted to show. So this is the printer, this is the cuvette with the resin, goes inside the printer, nothing happens, no physical processes going on, some light is being cast on the printer, it moves, and in a couple of minutes, we have this particular scaffold, and we see that something has polymerized inside the cuvette in the resin itself. And when you take this out, it's a aneurysm model. It's a medical disease where blood vessels get clots, and we can make those completely hollow organs, passing fluids inside those, depending on the thick and thinner wall, and this can be replicated. This is one of the examples. We are working on multi-complex organ structures that we can replicate inside the cuvette to make the process faster. Another use case in ophthalmology, so we are also working towards making prescription glasses, contact lenses, etc., and also in dental, but our main focus at the moment is more towards the organs, etc. And so why so far we are progressing? So this is a contrast of current state-of-the-art using xolography, where we see there is this continuously printing and polymerized. That's because of the cross-linking of the monomers in the vat, and which gives you a fairly isotropic, smooth surface, in contrast with those printed where layers are glued on top of each other, and this also makes it more prone and potential breakage points along those printed layers. And this is the wide range of materials we have already tested and did our print. So some of those, so this is from starting with the very hard acrylate resins until very soft hydrogels, Pegda, Gelma that we also built in-house. We have been synthesizing our new materials in there. I do have some of those printed objects with me in case somebody is interested to have a look how the final objects look like. I'll be happy to show those and talk after the session. So this is the wide range of material property on viscoelastic property we are working very successfully here, and not only that, we have been doing this in continuous flow, so it can go on for a scalable production level printing pretty soon in line in the flow, and we don't have to stop the production. in collaboration with the DLR, we have already printed at 0 gravity. Very successfully, we took our Zube in an aircraft beyond the gravitational level, where microgravity, and that's Nicholas, our head of materials, flying in the 0 gravity zone, and we have successfully already printed for our space applications. And wish would be also more towards printing around devices, organs on chips. We do have some medical projects around that. And all of this fascinating thing, how we are working, this is the basic working principle of our device. So it's a pretty conventional, any user-friendly CAD or STL file you load here, and then that's the cuvette, and the main technology is that two dual color photo initiation of the polymerization process. So UV goes from one end and the visible range, and the photo polymerization starts with the very thin light sheets that are being produced with the UV range, and then the visible light process, and in this, and the cuvette moves towards the inflow, and thereby the light sheets go on making projections, and you get the final 3D prints within the cuvette around this. So this is the final specifications of the products, very high resolution, 5 microns. I can talk more after the talk about our products, but this is Zube 2, which will be launched in a couple of weeks. It's up and running in our application lab. Some of you in biomedical field, if you're interested to explore, we have an application field, lab for hands-on experience. Please feel free. And doesn't move anymore.
I think someone stopped you.
Okay, no, I'm already done. So that's the part of our team. We are around 25 people at the moment. So the idea, the technology came from Stefan Hecht and Martin's work around 2020. And in 3 years, we now have 2 devices up and running, Zube and Zube 2. And Dirk is the chief commercial officer, and we are the bioprinting focused team. And I would be very glad to talk to people. I'm not so sure how many bio application enthusiasts are there in the audience, but I'm very happy to take all of those questions. Layerless, so ideal take-home message for you is it's a layerless, no support, and very super fast. It all takes from a couple of seconds to a couple of minutes to do, depending on the complexity of the structure. Thank you.
Thank you, Arpita. One very short question and a very short answer. Are the systems available? How much do they cost, and where can I buy them?
Yes, both are available. We are slowly taking off Zube off the market, and Zube 2 is next generation is already coming, and you can get hands-on as an early adopter. And so the Zube 2 that I showed costs around 85K euros, and depending on the add-ons thereafter it can go, but let's say the basic is 85,000 euros to start.
Excellent. Thank you very much.
Thank you so much.